Okay, well, welcome to the Thursday Tech Talk. So, I guess I'm going to make sure you sign in. And there's no CME credit for today's talk. Next month, Judy Zhang will be talking, I believe, about cap data on next month on March 2nd. And the following month, Michelle Crawford from you will present building smart systems to support healthy dietary choices in communities by leveraging cloud, mobile, and big data analytics technology. Okay, and then the ID, the Innovative Discovery Series, on February 17th. And Adam Marco from Jefferson, mindfulness interventions. And the presentations are on the Excel website. You can view the whole schedule according to there. So, I'm really delighted to welcome Han Ping for our presentation today. She's an assistant professor in the Department of Applied Economics and Statistics at the University of Delaware. She got her PhD from the University of Minnesota in statistics. And also her master's in applied computational mathematics at the University of Minnesota. Her research interests are, as you're find out here, in high-dimensional data, data reduction, statistical learning, quantile regression, which I'm sort of interested in. And she has actually, for being fairly brand new PhD, a fair number of publications of which she's the first author.
Thank you for the best introduction. It's my great pleasure to have the opportunity to visit the people at the Christian Center health system. And I would like to thank everyone for your precious time in listening to my talk. So the topic I'm going to present today is prediction and information inference in multivariate regression and applications to neuroimaging and bioassay. So my talk will be a little bit more methodological oriented, but I do want to show the potential applications in biomedical research and biostatistics. This is a joint work with Dr. Dennis Cook, and he was, because in this talk I will propose at least a technology called envelope. Probably you haven't heard about it. It was originally proposed in 2010, but took out an award in specific academia. The basic idea of enveloping is to identify material and immaterial information in multivariate analysis, and by eliminating redundant information, so we can achieve efficient gains in model estimation. So in this talk, I will introduce, illustrate this idea and extend it to the multivariate regression section. So you will see it shortly how it works. Here is the outline of my talk. I will begin with the background and the motivation of this project, and then I will introduce the idea of enveloping with a simple illustrative example to show in a setting of multivariate analysis, to show how we can use it to gain efficiency in hypothesis testing and in estimation. After that, I will propose a simple multivariate regression model and extend the ideal envelope into matrix setting. We call it as the matrix envelopes, and see how it can help estimation, improve estimation efficiency in this framework. With this preparation, after that I will propose a generalized framework of matrix regression model. So I will show that it actually can incorporate the classical regression model as a special feature. And we will consider the envelope structures with the estimation, some theoretical properties, and also some numerical performance. At the end, I will conclude my talk and present some future work. So why we start this project? The reason is that with the rapid development of modern technology, now dealing with matrix value variables. So you can consider that data with team-like structure data or big data are more commonly encountered in contemporary statistical applications. For example, now we may more often collect longitudinal multivariate responses or longitudinal multivariate predictors. So for such data, you can integratively treat it as matrix variables. Because the measurements on rows represent, the longitudinal information, the measurements on columns represent the multivariate information, the different characteristics. And also temporal and spatial data. It naturally forms a 2D structure, two-dimensional structure, with the row and the column represent the measurements over time and location space. Furthermore, imaging data, especially 2D imaging, like EEG data, it has a 2D structure. So for such complex structure, a conventional regression method, for example, conventional tools in multivariate analysis can be limited because modeling matrix variable data directly implemented. It shows certain advantages. For example, it can preserve the original matrix data structure. So if you model the matrix value data directly, you won't lose the temporal and spatial information. You can still preserve that information. And also, we can retrieve dependency information among the rows and columns separately. So you can consider the covariance information of the measurements over time and measurements over space, location separately. So by fully utilizing such matrix variate data information, we can actually reduce the number of parameters in estimation, so which can lead to efficiency gains in model inference. In addition, in matrix value data, since the messy information also exists, so redundant information is very likely to contain the data. We further propose the matrix algorithm method to identify such material and redundant information, and then eliminate the redundant information from estimation, so which can further improve efficiency. So our approach is likely to achieve two steps for efficiency gains. One is through matrix value regression, and another is through envelope listening technology. Before we move to the matrix value regression setting, because enveloping is a relatively new idea, so most of you are probably not familiar with it. I will begin with the illustration to show how it works. Just with a very simple example for the Berkeley Getting study. So we use this example as an illustration to show what's the envelope and how it works in this simple data setting. The data monitored girls and children born in Berkeley, California between 1928 and 1929. So in this study, 93 children were monitored, among them 54 were girls and 39 were boys. So basically, we monitor the growth of children, boys and girls, and want to compare, maybe if there's a real difference. So suppose here we only want to compare the height in centimeters between girls and boys at ages 13 and 14. Well, this is a simple two sample comparison problem, right? You can do two tests if you want to do this simple data analysis. So usually in statistical analysis, if possible, we would like to do a graphical illustration or graphical summary of the data first. Below is the scatter plot of the data at ages 13 and 14. The two axes represent height at age 13 and 14. And the dots are the joint distribution of boys and girls. So we use the dots here represent boys and the crosses represent girls. It's the joint distribution. And the two curves here are the marginal distribution of boys and girls' height at age 13. It's the marginal distribution. So basically, it's like you project the data. Basically, in the marginal distribution, you project the data onto the age 13, and you get the marginal distribution for each group, right? So you can draw a histogram, and then you smooth it. This is like a smooth marginal distribution. So you can see that jointly, the two groups are well separated. So there's a group difference if you look at it jointly. However, marginally, these two curves, two marginal distributions are much overlap, which means marginally you cannot test the statistical significance. But jointly you do see difference. So what's the problem? The question is, can we use the joint distribution information to make a statistical inference marginally more, make the testing on the marginal distribution more efficient? The answer is yes. But if you just use the traditional t-test, you are not, identify the group difference. But if you use envelope, the idea of enveloping, it have to achieve this goal. To illustrate the idea more precisely, we want to consider the population level distribution, because this is a sample level distribution. So it's like you collect the random sample from the population, right? But to present the idea more precisely, we want to consider the population level distribution. So you can consider this ellipse represent the distribution of boys. So you just imagine the observations are within this ellipse for boys, and the observation within this ellipse for girls. So this is the population level distribution. And we represent them with ellipse. Basically, we assume the data is normally distributed, is a bivariate normal. And these are the marginal distributions. Again, jointly you see clear separation, and marginally we don't see. We cannot hardly detect the significance. So the key point here lies in this black line, this direction. Because only this direction serves to distinguish the two groups. The reason is that suppose you project the observations of boys and the project observation of girls onto this direction. The projections from the two ellipses, they are well separated, right? However, if you project them onto this orthogonal direction, what you can see, they are totally identical, right? They are totally overlapped, which means that this direction is totally redundant to the goal of study. This direction does not serve to distinguish the two groups, because the projection, they are totally the same. And only this direction serves to separate the two groups, distinguish two groups. So this direction is the useful direction. We call it a material direction. And this direction is immaterial, is a redundant, immaterial direction. So this material direction is the envelope. We call it envelope. Actually, it's a subspace of the two-dimensional space. So we reduce the two dimension to one dimension, and this is the envelope. It's the material subspace. So to apply the envelope methods for the data analysis, what we do is that we only use the material information to perform hypothesis test. So how to do it? Basically, because we only want to use this material information, so we firstly project the data, from boys and girls onto this direction, to eliminate the redundant information project onto this direction. And then if we want to compare the two groups marginally, we project from this direction to x-axis. And in this way, we eliminate immaterial variation on this side, on this direction. So now you can see by using envelope, the two marginal distributions are much less spread out, which means it has much smaller variances. The reason is that we eliminated this immaterial variation. So if we go back to the sample data. Similarly, you can see that this direction is the material, right? Because when you project the boys and the girls onto this direction, the two groups are well separated. However, if we project onto this orthogonal direction, they are much overlapped, right? They are much overlapped. So this direction is immaterial, and this direction is material. This is the envelope. So to use the envelope for data analysis, we only use the material information. So we project each data point. For example, for this goal, we project onto the envelope first. And then if we do marginal analysis, we project from here on axis. axis. And then we repeat this procedure for all the goals. So project all the goals of this direction and project them to x-axis. So after doing so, the marginal distribution of goals will be like this. It's much less right, has a much smaller variance because we reduce this redundant information. Yes.
So how could you interpret this marginal distribution? That means the girls has in the age 13 dimension or
age 13. It's at age 13. So basically you project the data right onto x-axis. So you get the distribution. So you can draw like a histogram, right?
But you switch that dimension, right? You switch that. It's not that the. What I'm saying is, so traditionally we would like to use like a, just like you said, use the t-test to test how the group mean between the boys and the girls, right?
Yeah.
And when you do that transformation, what's your hypothesis gonna be? It's also
still we test the mean group mean. Still we are testing like the mean if the mean group mean is it doesn't change the traditional goal of analysis. We still achieve the same goal, but now we do a dimension reduction. We eliminate redundant information. So the hypothesis testing will be still the same. We test mu male is equal to mu female.
So the difference means at age 13 or at age 14?
It doesn't matter. You can test at age 13 or age 14.
Yeah, marginally we can test it separately, right?
Yeah.
But when you do that, when you do your envelope, so what the hypothesis means? So that means you test the difference with age 13 or with 14 or with both?
You can do either. You can test the age 13 or age 14. But the point is that when you do marginal hypothesis test, we still use the joint distribution information. So in the conventional analysis, if you do hypothesis testing at age 13, you just use the data observation at age 13, right? You don't consider the age 14.
Yeah.
But here, if we do hypothesis testing at age 13, we still do this. The hypothesis test is the same,
okay.
But now we use the joint distribution information.
But we borrow some information from age 14, right?
Borrow information
gotcha.
from the massive data.
Okay.
Yeah. To gain efficiency here.
Got it.
Yeah. So that's a very good question. Okay, so we project all the goals, onto envelope, and then we get marginal distribution. Because this projection, we eliminate redundant information. So now the marginal distribution has a much smaller variance, much smaller standard deviation. Similarly, we can do it for boys. I will project each point onto this axis, and then if you do marginal analysis, project again to axis. We repeat all this procedure for boys, and then you get a marginal distribution for like this. You can see now, because the variance is reduced, so the two groups are bioseparated. The means is still same, but the variance is reduced. And then you compare to the original marginal distribution without using envelope, you can see that, because the large variances, so originally the two curves are bioseparated. Now because the reduced variances, they are separated. So that's the efficiency gains. So we basically reduce the estimation variance, but the means are still the same. So you can see the centers between two groups are still the same. So that's the basic idea. And then if you do a t-test before and after using envelope, you can see that the t-test for the two group means of these dashed curves, the p-value is very big, right? Because you expect, you can't detect the significance. However, the t-test after using enveloping, after the projection, is close to 0. So it's a very, you do see significant difference. Now let's quickly summarize the idea. So the goal for enveloping is to distinguish material and immaterial information. The material which is for like line, the direction for like line, and immaterial which is orthogonal direction. And then use only the material information for model estimation and the inference. And by eliminating redundant information, we can reduce estimation variation. So as showed previously, we reduce the estimation variation, reduce the variances. And therefore, even without the large sample size, we can detect the statistical significance. this can lead to economical experimental design. Yes.
So in the example, I guess the way that I would think about that in more typical analysis would be to do a 2 by 2 repeated measures. So you would have 13, age 13 and age 14 for each student, and then you would have boys versus girls. So what would be so in the way that you're doing that is are you getting the same results, the same as you would doing the 2 by 2 repeated measures? I guess in one sense it seems like that's a really complicated way to compare the two groups.
Yeah, that would be. I mean, like if the data structure, I mean the distribution is still similar, then you do see you do observe the same result. But if you repeat measures, for example, there is some variation, then maybe there is some, some different results.
Yeah.
So yeah, here we didn't consider repeated cycling.
Okay.
Yes. But that's a good question. I mean, you can add a random effect, right? You can consider enveloping even with random effect. But so far we just consider the regression setting without random effects. So here I basically use a simple data example. So it's like a bivariate data to show the idea of enveloping. In fact, envelopes can be applied to more complex data analysis. For example, it can be applied to general multivariate linear regression, or applied to partially sparse to achieve prediction, more accurate prediction. And these domain analysis with structured regression, they can be very broadly expanded. And also, I here omit the technical details behind this idea. For example, in real application, you may need to estimate the envelope regression. You cannot exactly see which one is envelope, but you have to estimate. So that will involve some mathematical details. I will introduce the technical details in the citing of matrix vector regression technique. So now let's move to matrix vector regression. Again, I want to start with a real example called the EG data. So this is a typical neuroimaging data. Basically, used to have study the brain activities between like treatment or control group. So the data is open source. It's collected from UC Irvine, and it contains measurements from 72 group subjects. 77 were alcoholic and 45 were non-alcoholic, which is the control group. So for each subject, we collect some matrix measurements from 64 channels of the brain regions at 256 times. So basically, in this experiment, some electronic equipment were placed on the subject's scalp at 64 regions, 64 channels. And we measure the brain signal at these 64 channels over 256 times. Over 256 times. Then, ideally, in this data set, for each subject, we collect a matrix value of the measurements of dimension 256 by 64. With the elements that rows represent longitudinal information, 256 times the column represent the 64 locations, right? So here, for each subject, we have matrix value of the measurements. So that's different to the previous cycle.
So each subject has 264
by 256
rows.
By 64.
256 rows, right?
Yeah. So you have and we don't want to vectorize this because we want to preserve the row and column, the time and location column. And again, we want to do a two-group comparison. So we want to investigate if the matrix valued records are associated to alcoholism or not. So you basically want to compare the two groups based on matrix valued measurements. not a vector value. Well, a simple model. So in this setting, we do have repeating measures. You can use the traditional random effect model, multivariate random effect model, but here we want to propose the new tool, matrix regression tool. Here is the 3D plots. 3D plots for typical alcoholic and non-alcoholic subjects. So we have alcoholic on the left and the non-alcoholic on the right. And the two horizontal axes represent different times and different locations, different channels. And the vertical axis represent the voltage of the brain signals. So we use three colors to represent different ranges of the values of the brain signal. For example, the red represents relatively low signal, and the blue represents relatively high signal. So you can see that compared to the two groups, we do see distinct pattern, right? Distinct pattern. For example, for alcoholic subjects, the brain signals are relatively higher compared to the control. And in addition, the different signals appear at a certain location at certain times, not appear at all the times, all locations. This indicates that redundant information can exist. So envelope can be useful to identify, material information and achieve some efficiency gains. It can be useful in this matrix verification. A simple matrix variant regression model we propose here is like this. So here, y the response is the matrix value, that is R by n. So we model the matrix variant data simultaneously, directly. X is a univariate in this case because the X is an indicator variable. The 0, y indicating a subject is alcoholic or control. Therefore, mu is a matrix value intercept. Beta is a matrix coefficient. And the random arrow is a random matrix. So here we assume it follows the matrix normal distribution with the two covariance matrices, sigma 1 and sigma 2. Here, sigma 1 is called a column covariance matrix because it measures the covariance among the columns of the arrow. And sigma 2 is called the row covariance. It measures the covariance among the rows. So we measure the covariances of the data separately with the two covariance matrices. And because X is the indicator variable, it takes value 0 and 1. So we can show that the intercept actually at the population level is basically the group mean of the control subjects. And the beta is the group mean difference. So the difference between the average signal of alcoholic and the average signal of control. Because X is 0, 1, so you can mathematically show it. Then since we want to investigate if there is a group difference, right? So the goal here is to test if beta is significantly different from 0 or not. But the beta here is matrix value. So we do hypothesis testing. We want to test if beta is significant from 0. Well, if we don't consider envelope structure, we just do estimate this model, this structure. You can do maximum likelihood estimation. And at the end of the day, you can show that the beta height, the MLE of beta is simply the the sample mean difference. So just replace the population with sample mean, so just sample mean difference. And we can derive the asymptotic variance and you can perform hypothesis test. So this pretty similar to the measurement. But the asymptotic variance is different. However, now we want to use absolute methods to identify material and immaterial combination and see if we can achieve some efficiency gains in hypothesis testing. So here is some mathematical component for the idea of enveloping. I will try to explain more intuitively. So because for matrix value data, the redundant information can exist in both row and columns of the data. So we want to use two envelopes to identify the material part of rows and columns separately. So here we have a column envelope denoted by epsilon L and a row envelope denoted by epsilon R. to capture the material part for rows and columns. So mathematically, they are defined as the smallest subspace. Recall in the Berkeley guidance study, the envelope is the black line, right? So it's a direction spanned by the black line. It's a one-dimensional subspace. But in general setting, the envelope can be, two-dimensional, three-dimensional subspace. So here, we define them as the smallest subspace that satisfies these two conditions. So here we use the P epsilon L, P epsilon to denote represent the projection matrix onto the envelope, and the Q epsilon to represent the projection onto the orthogonal direction. Then the first condition means that when you project the columns of Y onto the orthogonal direction of envelope, this part is distributionally equivalent to the conditional distribution. So which means this part does not depend on X. No matter X is 0 and 1, this is the same. It's the same. Therefore, this is the immaterial part. This is the redundant part. So if you go back to the previous graphical illustration, this condition means that when you project the Y, columns of Y onto this orthogonal direction, right? This is orthogonal direction. While the projections from goals and boys, they are the same. So this means this part is redundant. This is immaterial. So this is exactly mathematically defined the immaterial part. And then if this is immaterial, then this is the orthogonal part. This part will be material. So the second condition means that given for each group, the material and immaterial part they are uncorrelated, which guarantees that mathematically guarantees that the material part is sufficient to estimate the group mean inference. Guaranteed is sufficient.
So, is there possible you can always find the material space? I mean, contain all the information. Since if two-dimension look like here is parallel, so you can find just like the linear discrimination. So you can find that subspace or small space. However, if the data is a little bit messy,
Very good question. It's not guaranteed always you can find the subspace. Sometimes you may, in some data sets there may be no redundant information. All the data information is material. But when the dimension of the data goes too high, there are always.
So there's some way to determine that, right?
Yeah.
Okay.
Yeah. I will show later. We will how to determine the envelope dimension. But it's more useful in high-dimensional big data because when information is massive, there are always some redundant information.
Yeah. Also,
all the information is
also the number of the smaller space. How, what is the?
I will. Yeah. Maybe I will show how.
Okay. All right.
It's very good. So the first condition define the material part, which is the column, the material part for the columns of the data. And then the second, similar, define the material part for the rows of the data. So that's how we define the row and the column envelopes. And mathematically, we can show that the first condition is equivalent to say the column span of beta is contained in the column envelope. So that's why we call it envelope, because it covers the column space of the parameter of interest. So that's why we call it envelope. It covers, incorporates. And in addition, the column covariance can be decomposed to two parts. So this is the material variation, this is the immaterial variation. And similarly, condition 2 mathematically equivalent to say the row span beta is contained in the row envelope. And the row covariance has two decomposition. So this result will help us to formulate the matrix, the envelope model. Here is the envelope model. Because the envelopes are subspace, so they can be characterized, they can be determined by semi-orthogonal basis, right? How do you determine subspace? You use the semi-orthogonal basis to represent the subspace. So here we use L, which is R by U1, and M by U2 to denote the semi-orthogonal basis of the envelope subspace. And we use L0 and R0 to denote the orthogonal basis, so which is the basis of the immaterial subspace. And since from the previous condition, we have shown that the column span is contained in the column envelope, and the row span beta is contained in the row envelope. Then we can reparameterize beta into a coordinate form with the eta as the coordinate relative to the basis of the envelope, right? Because it is contained in the space, so you can have this coordinate form. So these are the envelope parameters. And similarly, since the sigma 1, the two covariance has a decomposition, we can also have a coordinate form relative to the envelopes and orthogonal directions. So this is the envelope model. And these parameters, all these parameters are envelope parameters. So again, our goal is to estimate beta. We are not interested to estimate this envelope parameter. We're still interested in estimate beta. But once you estimate the L, eta, and R, then you know beta, right? So we estimate the beta through the envelope parameters. And you can see that in this envelope model, we directly connect the parameter of interest to the information that is material, right? Because these are the material, these are the envelope. So we connect the parameter of interest to the material part, to only the material part. Here goes to your question. So, well, L, the envelope basis is R by U1. So U1 is the envelope dimension. R is the full dimension. So U1 is usually less than equal to R because we're looking for the subspace. And the U2 is the dimension of the row envelope. So how to determine U1 and U2, right? Well, we can consider them as model selection parameters. So because all the possible U1 is that U1 can take it from 1 up to R, right? 1, 2, 3 up to R. So that's all the possible values for U1. And the U2 can take 1, 2, 3, 4 up to M. So we do model selection. We consider all the possible R and all the possible U1 and U2. And then we can use information criterion, for example, AIC and BIC, or likelihood ratio test to select the optimal envelope dimensions. Just like when you do linear model, how do you select the variables, important variables? You do AIC, BIC, right? You do forward, backward selection.
So you do the graded selection, right?
Yeah, we do the same thing. We do model selection. We use the AIC, BIC to select the envelope dimensions. So we learn all the information from data. And actually, because under normality presumption, this is consistent, guaranteed the selection is consistent. So for this model, we can use maximum likelihood estimation. We estimate all the envelope parameters, and once we know the envelope parameters, we know beta. So I'm going to omit the estimation details because we have flagged this two-step iteration activity. So here are some theoretical results. Well, we use the beta OLS, the ordinary least square estimator, to denote the standard estimator without enveloping. And then we use beta height to denote the envelope estimator. So at the end of the day, we can show that the beta height, the envelope estimator, is actually equivalent to the standard estimator, the projection standard estimator of the two envelopes. So if you know the two envelopes, basically you estimate beta using the standard method, and then you just project it onto the two envelopes, project it onto the material part. Then you gain efficiency because you limited the reduction information. For standard estimator, we know that it's a Newton consistent and asymptotic normal. For envelope estimator, we can simply show that it's also Newton consistent, which means that when sample size n is large enough, the estimator is converted to the truth, and it's asymptotic normal. So we can have a splitting formula to calculate the asymptotic variance that can be used to do hypothesis testing. Because once you know estimator, you know standard error, you can do normal test or t-test. More importantly, we proved that the envelope estimator is asymptotically more efficient than the standard estimator, which means the variance of envelope estimator is always smaller than or equal to the standard estimation values. So that's kind of confirm our previous observation. And the efficient gains can be massive when the immature information is large. Because the immature part is larger, you eliminate more redundant information, so the efficient gains is more obvious. Okay, now let's go to evaluate this new method by the real data, see what's the numerical performance. So recall that in the EEG data, the response is 256 by 64, is a matrix valued brain measures, and the predictor actually is a 0-1 indicator function. And we want to explore if the brain signals, the matrix valued brain signals, are significantly different between alcoholic and control groups or not. So we want to test if beta is significantly different from beta. And we apply the likelihood ratio test to select the envelope dimensions. It suggests that the U1, the column envelope, the dimension column envelope is 15, and dimension for row envelope is 7. This indicates that among the original 256 dimensions, only 15 directions are useful. All others are redundant. And similarly, only 7 of out of 64 are useful, valuable. The rest of the direction subspace are immature, redundant, totally redundant. And then we apply the standard estimation and the envelope estimation for the analysis. Here, this table is the standard estimator, envelope estimator, and the corresponding standard errors, estimated standard errors. So you can see that the estimators are pretty similar, no deviation large, because they are both root-term consistent to the truth. So the estimator is similar, but standard errors, well, the standard errors of envelope method is much smaller, right? Which confirm our previous theoretical results, because we have shown that the variance of envelope estimator are always smaller than conventional. And the relative ratio between two range from 1.8 to 7.2. So the gains is pretty massive. And we do a hypothesis testing for the standard estimator and envelope estimator. Because the standard error is reduced, so when you calculate z-score, which is the ratio between the two, well, now the z-score for envelope method is more significant. However, standard method, you hardly to see significance, right? Because when the absolute value of z greater than 1.6996 is significant. So you can see here, we do see more significance, but standard method cannot have that. Now recall that beta is a matrix value, right? Beta is 256 by 64. So here we just list the first 5 results of beta. But the rest results are similar. Well, you may ask, you may raise some question. Here you are doing multiple tests. How do you control the type 1 error? Right? So we have a last test, 256 by 64. We further adjust the type 1 error by false discovery rate. Because we are doing multiple tests, so we apply the false discovery rate to adjust the p-values. And this plot compares the p-values after the false discovery rate adjustment for alcoholic and for non-alcoholic subjects. The horizontal axis represent the result at different brain locations, and the vertical represent the transformed p-value. We do minus log time transformation of the p-value, and this dashed line is the 0.05 significance level, and above the observation above this line indicates significance, below indicates non-significance. So you can see that using with enveloping, we can successfully identify 2 clusters of brain regions that are significant, which means they are different between for alcoholic and non-alcoholic subjects. However, with the standard method, we cannot hardly detect any significant brain regions. So that's some numerical result, which is confirmed. Just the random result. So that's the efficient case. That's the efficient result. Next, I'm going to briefly introduce the general framework of matrix value regression, because in the previous setting we assume Y is the matrix value, the X is the indicator, X is the univariate. However, for more complex data, you may encounter both response and predictors are matrix value. In this case, we propose a new matrix value regression model that has a bilinear coefficient form, bilinear coefficient form. Because Y and X are both matrix value. So beta Y, we call it as the column coefficient matrix because it captures the relationship between the columns X and the column Y. And the beta 2 is a row coefficient matrix. They capture the relationship between the rows of X and the rows of Y. And again, epsilon is a random matrix. So other parameters are same as before. And this model actually incorporate simple regression, multiple regression, multivariate regression as special cases. Because when Y and X are univariate, beta 2 vanishes, so this model reduced to simple regression. And when Y and X are vectors, again beta 2 vanishes, so this is reduced to multivariate regression. So this is a general framework for more complex structure. And to apply our methods of this model, the idea is similar. The only difference is that we now use column envelope to envelope beta 1 and the row envelope to envelope beta 2. So we envelope them separately. Therefore, beta 1 and beta 2, they have a coordinate form corresponding to the two envelopes respectively. And all other settings are the same. And the estimation, model selection is exactly similar. Theoretically, we can show that envelope estimators are root consistent to the truth and asymptotically normal, which help us to perform hypothesis testing. And they are asymptotically more efficient than the standard estimators. And in fact, we can further prove that our methods, our estimators, are robust to normality assumption, which means that when you select the random error to be non-normally distributed, the consistency, asymptotic normality, and the asymptotic efficiency is still hold. As long as the random error has a fundamental false moment. So we next really evaluate the numerical performance of the general matrix value regression model through the bioassay data. So in this data set, it's a term crossover assay of initially regarding blood sugar concentration of rabbits. So in the experiment, 36 rabbits were collected, and they are randomly classified, randomly partitioned to 4 groups. And then some treatment, 2 different treatments at the 2 different dose levels were assigned to the 4 group of rabbits over 2 days. And then we measure the decrease rate of blood sugar concentration over 5 hours among 2 days. So here we consider the response as a matrix of 5 by 2, which represents the decrease rate of blood sugar concentration after receiving the treatments at 1 to up to 5 hours over 2 days. So we consider all the measurements integratively as a matrix. And then the predictor X is a 2 by 2 matrix. So it represents the 2 treatments at the 2 dose levels. We apply the matrix value regression to this data, and we compare the estimation variance of the standard estimator and the envelope estimator. You can see that the envelope estimator has much smaller variances, much smaller standard error, because we limit more redundant information. And the likelihood ratio test select the envelope dimension is 1 on the columns, which means among the original 5 dimension, only 1 dimension, 1 direction used. We further compare the prediction performance of the standard method and the envelope methods. So here, there's the dashed line denotes the prediction errors of envelope model at the different envelope dimensions. And this solid line represents the prediction error of the standard method. Because the standard method it does not depend on envelope dimension, so it's a constant. However, the envelope method does depend on the dimension, right? Dimension of the subspace. So you can see that the envelope method outperforms standard method over all possible envelope dimensions. And at the optimal envelope dimension, the prediction error reaches the minimum. And then when the envelope dimension increases, you incorporate more redundant information, so the prediction error increases. And then when the envelope dimension is equal to 5, when it's equal to the full dimension, it means that there's no redundant information can be eliminated. So the envelope model is essentially the same as standard model. That's why the prediction error they coincide. So that's the numerical performance. We do see efficiency gains. Here it's a quick summary of this talk. So here are some take-home messages that I want to deliver. And in this talk, I introduced the enveloping idea of enveloping. This is a recent technology that is served to improve efficiency in estimation without changing the traditional objective. So we still want to prepare truth rules. We still want to estimate for the coefficient matrix, but by eliminating redundant information, we keep the efficiency. And we propose the general framework of matrix variety regressions and extended envelopes to matrix variety analysis for efficiency needs. The key idea of matrix envelope is that we distinguish material and immaterial information in both rows and columns of the column space of the data, and then use only the material information for the estimation, which again improves efficiency. So at the last step, I want to introduce some ongoing and future works and my research areas. So there are two major directions in my current research. One is the envelope models, and another is the sufficient dimension action method. In the envelope framework, since it is a totally new idea, totally new technique, there are a lot of things can be done in this area. For example, we have recently studied the envelope methods for content regression. As you may know, content regression is a valuable complement to conventional mean regression. So it can help you to measure the association between the response and the covariates at the different quantiles of the data. So you gain more comprehensive picture, right, about the associations. So content regression has a very important application in biomedical study. For example, study the birth rate or other medical characteristics. So we have applied envelope, extend enveloping to content regression, and we showed that both theoretically and numerically showed that the envelope content estimator is asymptotically more efficient than the standard content estimator. Also, I'm interested to study censored data in survival analysis. Again, we propose the censored envelope content regression for censored data analysis. This can have an important application in survival analysis. In the future, I also plan to study envelope approach for missing data with measurement errors. So they are all commonly important in biomedical studies. In the second direction, sufficient dimension reduction. So this is a relatively older area compared to envelope method. Sufficient dimension reduction is an important tool in statistical learning, data mining. Basic idea is that for big data, for high dimension data, we want to project our data dimension to a low dimension. And then, once you reduce data dimension, you can more efficiently to apply conventional regression or classification methods. And this is a non-parametric. So this is a distribution free compared to envelope model. So they are different. And I'm currently studying tensor sufficient dimension reduction from neuroimaging data. For example, MRI or functional MRI data. Because for MRI data, you collect 3-dimensional, 3D measurements for each subject. So it's more complex compared to EEG case. So we perform sufficient dimension reduction with the brain region selection for MRI data. And also, we are interested to study high-dimensional SDR for count data. This, RNA sequencing data can be considered as a count data, right? So it has a very important application for RNA sequencing. Actually, I just submitted a grant proposal. So with this approach, and we want to investigate how it performs for RNA sequencing. And if you have some data set, you are interested for collaboration, I'm going to be happy to talk with you. Because I'm now looking for RNA sequencing data, good RNA sequencing data. And at the last, I'm also studying high-dimensional SDR for high-dimensional sensor data. And this is a very hard topic, actually, in current literature, because just recently there are a lot of work proposed for like a variable selection or variable screening for high-dimensional sensor data. I think that will be very interesting, very important area, and our method can make a good contribution to the literature. So I do, although I'm more theoretical, more methodological side, but I do I am very interested in potential application in biomedical areas of biostatistics, and I think this method has the potential. Here are some key references. The first paper, Cook et al. In 2010, originally proposed the envelope, idea of enveloping. And then these are some my recent work that related to matrix value data and matrix value regression envelopes. And this last one is also good reference. So that's all about my talk. Thank you very much.
So you mentioned in one of your last slides applying these methods, these envelope methods on missing data. What would be the goal, or what? I'm not quite sure I understand what you would like to find, or how you would. Yeah, what would be the goal?
Yeah, my thought is that because in literature there are already a lot of tools for missing data analysis, but they do not consider dimension reduction. They do not consider just do the conventional estimation and inference. I think envelopes can be potentially applied to missing data. For example, we just incorporated the envelopes information to the missing data modeling. For example, in my previous case, I incorporated envelope to regression analysis, right? But for missing data, there are different tools. And I think envelope can be potentially embedded to those conventional tools. So the goal will be the same. The goal will be the same, but by incorporating envelope structure, I think the estimation, the inference will be more efficient. For example, we just reparameterize the parameters in the missing data model, and I estimated all the envelope approach.
I think there will be a lot of applications for us, because when we do analysis of electronic health records, reading data sets from electronic health records, missing data is a major issue.
Oh, so what current approach do you use for missing data?
We ask Paul.
You do like a probability weighting or commutation, imputation?
Well, you do multiple imputation if you can assume the data missing random, but a lot of medical data is not.
Yeah.
Like, for example, patient-reported outcomes. Because that's dependent on how well or how they're sick.
Yeah.
And And there are methods, although in my experience that you can use imputation, assuming not missing a random. But in at least in the data sets that we've done that, you actually don't get that much difference in the results.
So you mean it's really robust?
Yeah.
Okay.
But so that's primarily the thing they did with it is that they don't missing data.
Yeah.
If it's a very small one, I guess I can. Sometimes the business is quite large.
Yeah. Then.
But I mean, I have at this point I really have no concept of how to apply this to this data, but I would be very interested.
Yeah. I just have the idea, but haven't explored into details. But I think in the future I would definitely want to learn more methods in the literature and see how.
So one of the